Guozhang Wang is an engineer at Confluent, which offers a stream data platform using Apache Kafka. Guozhang Wang, welcome to Software Engineering Daily.
Thank you, Jeff. Thank you for having me.
What is Apache Kafka?
So, by its definition, Apache Kafka is a distributed PubSub messaging system that it can be used as like a pipeline backbone for our for any online or real-time messaging or pipelining purposes.
Jay Kreps wrote a blog post on Confluent where he said, quote, "We built Apache Kafka at LinkedIn with a specific purpose in mind, to serve as a central repository of data streams," end quote. What is a central repository for data streams?
Yeah, I can maybe briefly talk a little bit about the why we built Kafka at day one at LinkedIn.
Please.
So myself is also having worked at LinkedIn for a couple of years before I became an engineer at Confluent. So we also have been working heavily on Kafka, and I serve as what we call it as the pipelining backbone for all LinkedIn data. So the context is the following. So at LinkedIn, we have a lot of data that are generated at our online services. Like we generate user activity tracking data such as page views, impressions, etc. And we also collect a lot of server logs and metrics such as syslogs, request rates. And at the same time, we also generate a lot of like emails or news feeds. And we have, again, some like computation derived data that are from our Hadoop clusters or from our data warehousing results. And we build a lot of the, we call it the data products around those collected data, such as, searching, recommendation systems, monitoring, if you have look at who viewed my profile, who have my job recommendations or things like this are all built around those data. So one key problem at that time that we ask ourselves is that how we can make those collected data to be available to those data products as soon as possible. Okay, so before we developed Kafka, the solution is sort of, we call it a point-to-point pipeline, where each service that generates the data basically make a contract with the service that actually are consuming those data. So like two teams may use ActiveMQ, or they can be using as simple as like a tail program or a simple Python or shell script to tell their data and pipe to the other product or the other team to consume and to make use of it. So
right, and so in that blog post, Jay Kreps highlighted two problems that Kafka aimed to solve.
Yep.
The first is transporting data between systems, and the second is doing richer analytical processing. So why didn't existing systems do this when Kafka was first developed? Like, what were the things that you needed to overcome in your development of Kafka?
So I think one major point at that time is the volume of data itself, right? So when we considered developing Kafka to actually meet our needs, like people use different systems to do their point-to-point pipeline, like I mentioned before. Like they use ActiveMQ off the shelf, or they can use commercial messaging systems, or they use as simple as like a PTEL or any other shell scripts. All those systems lack one key point, which is handling high throughput of the data volume. And that is also one motivation that they basically have to use their own systems only for one purpose or one type of their data. And the one disadvantage of such a architecture is that because we need to maintain all kinds of those systems for different needs of the data pipelining, its management cost can be very, very, very high. And it will be actually ideal to have a centralized pipeline backbone that basically can serve all kinds of those data as quickly as possible to serve to our data products. And of course, to do this, we basically need to design a new system that can be as scaled as possible to really handle this large volume of data.
Okay, so let's talk a little more about those two problems that Jay highlighted. So the first one, how does Kafka improve transportation of data between systems?
Okay, so I can maybe start from like the traditional solutions to like data transmission, right? So traditionally, people basically build their real-time or messaging systems by really buffering the data, and so that the consumers of those messages or records can get the data as soon as possible. So we achieve so-called real-time mechanisms for the messaging. But one disadvantage of using main memory for buffering the data is, of course, you basically lack the durability of your messaging systems. So, for example, if your consumer is lagging behind, or it has some back pressure that is processing the data slowly, the buffer data can actually explode in the messaging tier, or it will be dropped eventually, so that you can actually have some data loss. So one key thing that we consider is to have the durability in our messaging system as like the first citizen. And to do that, we basically use what we call the commit log, and that to do that with a append-only behavior, so that the data is persisted at the disk level or persistent storage, as well as achieving the low latency and high throughput at the same time.
So you're saying that it sounds like the most important thing was, first of all, durability. What are you improving in the transportation of data between systems? Mm-hmm. Durability.
That's right.
Which is manifested in this idea of Kafka as a distributed commit log.
Mm-hmm.
So let's go into the second problem that Jay highlighted, which is richer analytical processing. How does Kafka allow for richer analytical processing?
So first of all, for richer analytical processing, I think the key word here will be various types of different data processing patterns. So each message can take as small as maybe 1 microsecond to process, and can be also take as large as even seconds to process. So that is, I think, in my mind, what we call the richer processing. And because of that is again back to the first topic, that we really need to actually allow the consumers to basically consume or subscribe the data at their own pace. So again, to do that, we basically need to say, okay, if you are lagging behind the producing throughput, that is fine. We still need to persist the data, so that when you catch up or you change your logic, that data is still there for you to make use of it.
Let's go back to basics. What is a messaging system?
Okay, so that is a good question. I think messaging system, I think back to the 80s or even 70s, is mainly at like the transportation layer, where a messaging system is when you have like logically a queue, where the producers of this messaging system will basically put data into the queue, and the consumers will be get data from the queue, and each message can be consumed at most once by one of the consumers to this queue, and at the same time you can have some different patterns such as pops up, where basically the key difference is that one message can be consumed by more than one consumers in this manner. So any consumers that subscribe to this queue will get the message that is ever being published into this queue.
Right. So could you talk more about the network transportation layer of a messaging system?
Yeah, so the network transportation layer, usually it basically is composed of like some TCP protocol or some Unix send file APIs to just to send the data as like using the send file APIs, and so I think traditionally we don't have a concept of so-called a broker, where the producer and the consumer are sort of like interacting immediately and using some in-memory caching to buffer the messages that is sent to the consumer but not being consumed yet. And in Kafka, we introduce this so-called messaging broker, which is served to persist the data and to handle the requests from both the producer and the consumers.
How does Kafka fit into the broader data warehouse architecture as a whole?
Okay, so I can maybe talk about that in three aspects, right? So, like, I think Kafka can be used as a messaging system for at least three aspects. One thing is from online data to offline data. For example, like when I say that back at LinkedIn, we actually generate a lot of the online data, such as page views or impressions. Most of them will be eventually piped to our offline warehousing of Hadoop clusters. So Kafka in this case will be consumed by our ETL systems that actually can get the data from Kafka and pour that into our HDFS system that it will be eventually be processed using our batch processing layer, such as Hadoop or any other system like Jira, etc. And those ETL tier can be Camus or Goblin, which are open source, or which people can use some other ETL framework to do this data porting. And another aspect of using Kafka is to have online to online pipelining, where the data is generated on our online services again, but they are also being consumed by other online systems, such as such as like emails or news feeds. So this again can actually be formed as one use case of Kafka. And a third aspect I want to mention is to actually have offline to online pipelining, where the data is really generated from our offline data warehousing systems, and they can be pipelined using Kafka to our online data, such as like the machine learning results that are computed daily or weekly, and then be pushed into our online services to serve the user requests.
Kafka is summarized as publish subscribe messaging rethought as a distributed commit log, as we've already stated. Mm-hmm. What is the analogy between messaging and a distributed commit log? Why is it useful to think in that comparative term?
Okay, so I think the analogy here is that for messaging systems, you can view of its publishing as appending data to this logical queue that will be consumed eventually by the other end, which are the consumers, right? And back in the the database community or distributed systems, a distributed, or we can call it a centralized commit log, actually have the similar characteristics where all the writes are append only, where you don't actually override the values, so you already have into the system. You only append new data records into the system. So this actually aligned very well with the characteristics of a messaging system, where you do not need to you do not ever override the values you have already published to this messaging system or PubSub messaging system. Instead, you only append new messages into it. And the benefits of doing so is that, again, because we need to persist the data onto disks, having the pen-only behavior can actually allow us to make best use of the disk, which is sequential writes and sequential reads.
Fascinating. Okay, what is the difference between messaging and streaming?
That's a very good question. So I think for streaming systems, it actually have to be from two folds. The first one is actually, of course, a programming framework. So people should be able to have expressiveness power to easily programming their logics, such as per record processing, aggregates, and joins, etc. So again, the first aspect will be having a programming interface, so that the users of this streaming processing system or streaming system can easily express their computational logic. And the second aspect is to actually abstract the underlying distributed details from the end user, such as data parallelism, resource management, and monitoring. If there is a failure in one of the processors, the system framework should to be able to detect the failures and restart the task in some other nodes or resume it when this node has been recovered. So that is, in my mind, I think about as a streaming system, and a messaging system is really like the underlying data storage layer underneath a streaming system. So if you take an analogy from the real-time world with the offline world, which we have HDFS as our storage layer, and have Hadoop, and we can have some other batch processing system as the computational layer. So messaging system is like the real-time world HDFS, which is served as the data storage layer, and the streaming systems built on top of the messaging system really provides the programmability for the end users and hide those distributed characteristic implementation details, while the users need only to focus on their computational logic.
So would you say that messaging is like the plumbing of the streaming architecture?
Yes.
Discuss the basic vocabulary of Kafka. Mm-hmm. What are the topics and producers and consumers and brokers?
Okay, so the basic concepts in Kafka, I think I can summarize as follows. So first of all, the Kafka is composed of one or more, we call it the messaging brokers, that serves as like the persistent storage for the published messages, and as well as the service for serving both the produce request and the consume request from different clients. And on the client side, we have the producer client, which produce messages into the messaging broker, and the consumer clients, which consume messages from the messaging brokers. And each of the data that is getting produced and consumed have their own topic. So that is also a key concept of a publish and a subscribe system, where the producer, whenever it sends a message to the messaging broker, needs to associate a topic with this message, and consumers will just subscribe to one or more topics. So whenever a message has been ever produced with the subscribed topics, it will be pipelined to the consumers. So, and that is the concept of a topic, and each topic is again partitioned at the messaging broker layer to achieve data parallelism. So the partitions of a topic can be actually spanned across multiple messaging broker machines, so that when we have a larger and a larger data volume, we can simply horizontally scale up by adding more machines and having more partitions for our topics, so that it can actually handle the increasing volume.
Talk a little more about those partitions and how Kafka performs sharding.
Okay, so again, what a partition is like a concept of a topic. So when users create a topic, they can specify a number of partitions as the initialization process, which will be created and automatically span over all the messaging broker machines. And later on, user can add more partitions or shrink the number of partitions for this topic. Okay, and at the producing side, when users send a message to the specific topic, the producer client will determine which partitions this message should go to for this topic. And the partition is usually determined either by a user specified partition ID, or it is determined by the message key, so that all the messages with the same key will be sending to the same partition. So that is another characteristic of Kafka, where we preserve the ordering of messages at the granularity of per partition.
In the 2011 paper about Kafka, there's a distinction that's made between application data and log data, which is in like user behavior. So this distinction has become less clear over time. Is Kafka still viewed as a log record messaging tool?
Okay, so I actually agree with your point that I think this distinction has been quite blurred over the past years. When Kafka was originally developed, it was mainly served as for logging data. What I mentioned before, like system logs or request rates that we collected as metrics from our servers. But over time, we have seen people, using Kafka also for different application data, such as, I have talked about user tracking data, and I also have talked about online messaging data, such as emails and news feeds. So I think now Kafka has been actually used for any kinds of online type data, or I can mention them as like real time data messagings, which is maybe even already beyond the log data or application data.
Right. So messaging typically has two models. You've got queuing and you've got publish subscribe. And with queuing, a pool of consumers reads from a server, and each message goes to only one consumer. And so in queuing, maybe you have a list of tasks that the server just needs accomplished just once. And then in PubSub, the message is broadcast to all consumers. And Kafka has a single consumer abstraction called a consumer group that generalizes both of these uses. Talk about consumer groups and how they were conceived and how they deal with both of these models.
Yeah, of course. First of all, I want to maybe mention why we choose to have a PubSub protocol for Kafka. So that is like you said, in queuing system, each message will be consumed by one of the consumers and get processed. But the truth is that in many cases, a single message needs to be maybe consumed by different data products. For example, a page view record may need to be consumed by some underlying machine learning applications to do the data analytics, and at the same time need to be consumed again by some other online data products, such as recommendation or search product. So we really need to design the system so that a record can be consumed by different consumers for different processing purposes, and then moving forward, for each different purpose of the consumption or for each different processing logic, we define this consumer group, where each group can again subscribe to one or more topics, and the consumers within that group will get the message of the subscribed topic, but the message will only be consumed once by one consumer of the group, so that no two consumers from the same group will get the same records. This is how we achieve the data parallelism at the consumer layer. And the way we define the data parallelism is, again, at the granularity of the partitions, such that the partitions of the subscribed topic will be assigned to the consumers within the group, so that each partition will be consumed only by one consumer at a time.
How does Kafka relate to protocol buffers and Apache Thrift?
Okay, so I think for protocol buffers, Apache Thrift, and also like Apache Avro, those systems are serving as like a data serialization or data standardization systems, where you can put any type of records from your applications and serialize them and deserialize them while piping them through the messaging system. For example, Kafka have been heavily used Avro in the past for doing this kind of serialization and deserialization, and those mechanisms are usually done by a so-called schema of the message, so that for different types of data, users can define the schemas of those messages, which can be used by the system to do the serialization and deserialization. And then from the Kafka point of view, it's simply bytes in and bytes out. It does not need to be aware of any of the data schemas, so that we can achieve various data types sharing one single pipeline system.
Do Storm and Samza and Spark all use Kafka in the same way?
I think they use Kafka in pretty similar way with some minor differences. For example, I can talk about like Samza. compared with Storm, where for Storm, they use Kafka as the end system, where basically Kafka is only used for the source and the sink of the whole topology, right? And then for Samza, people can actually usually define their topologies with Kafka also storing the intermediate results as well. But I think generally speaking, those streaming systems usually use Kafka in a similar way as the underlying storage engine for their plumbing logic.
Right. So, and then maybe we could relate Kafka. I know you talked a little bit about these earlier, but how does Kafka relate to, or just compare to, message queuing systems like RabbitMQ or ActiveMQ?
Yes. So, actually, before the team at LinkedIn have decided to develop Kafka, we have also done some study on ActiveMQ and RabbitMQ to see if actually back in time, if those systems can meet our needs. I think one difference between the later designed Kafka with ActiveMQ or RabbitMQ is that for those systems, they were not originally designed for the data volume that we actually have seen today, which can be 2 or 3 magnitudes larger than the traditional messaging system or database systems. And because of that, most of those systems are designed to buffer the data in memory because of the small scale of their data they need to handle, so that they can achieve real-time processing real-time messaging. And again, for large volume and also various different data types, this design have a few disadvantages. One is, of course, because of the data volume is so large, they cannot really afford to always buffer their data in memory. And because of the different processing logics, the need for persisting their data so that they can be later consumed and reprocessed, and also to be stored for handling like back pressure or consumer and logic errors is getting more severe. So that I think this is one of the main differences that we saw this system compared with Kafka.
You are an engineer at Confluent, which offers a stream data platform that uses Apache Kafka. Mm-hmm. What is Confluent?
So Confluent is we think of ourselves as a real-time stream pipelining frameworks provider that is built around Apache Kafka, so that people can leverage to build their own real-time systems for their needs.
And the purpose of managed data warehouse services like Confluent or Cloudera or Databricks seems to be that these services are extraordinarily hard to configure. How does maybe I'm incorrect. Maybe that's not what Confluent's motivation is. But how does a customer of Confluent communicate his requirements such that Confluent can go configure what the customer is asking for?
Okay, so I think I share your point that for systems like as complex as Kafka and as well as Spark and also Hadoop, configuration such systems is always a pain, such that you need to know how to operate, and you need to know how to troubleshoot, etc. So for Confluent, we provide like tooling and also enterprise class platforms that is built around Kafka, such that we can actually make this a lot easier for users to just to focus on their application development and simplify the ongoing operations. And the way we approach it is to actually build first of all, we build ecosystems around Kafka. For example, we have mentioned like Avro or Thrift or Protocol Buffer as the serialization and deserialization systems. These systems can be supported out of the box for users to really do the data serialization for them. And the second example of such ecosystems will be some REST proxy, where users that is not actually using, for example, Java for their client can easily interact with Kafka to publish and consume data from.
In that blog post that I mentioned earlier, the blog post that Jay Kreps wrote, he described the world as it was when LinkedIn was first building Kafka, and it sounded like a nightmare. To quote him, the complexity meant that the data was always unreliable. Our reports were untrustworthy, derived indexes and stores were questionable, and everyone spent a lot of time battling data quality issues of all kinds, end quote. Is this a common case among Confluence customers?
Yeah, I think it depends on like the size and the types of data that I think our customers are collecting using Kafka or any of the pipelining system. I think for LinkedIn, because like I said, we actually we need to collect all kinds of different online data and as well as offline data. We need to make them available to our various data products. Having like one unified system to handle such problem can become very tricky. And as I said, before Kafka was really introduced, people just use their own solutions between each pair of a point-to-point producer and consumers, and that can actually be very tricky to maintain for the first thing, and also hard to troubleshoot because you have this variety of characteristics of the system that you need to train. For Confluent customers, I think depending on the scale as well as the variety of data types, they can be a similar issue for them as well.
If Confluent had existed as a company when LinkedIn was building out its data warehousing, and LinkedIn came to Confluent as a customer and said, help us, we have these problems, what would the process be like for onboarding LinkedIn as a customer?
I see. I think the way we onboard our customers at Confluent will be, first we need to really understand very well about the scenarios of the pipelining problems that our customers are facing. For example, back in time, LinkedIn was facing this problem that Jay has already been describing as not durable, or I should say it as not persistent data collection, and also because of the in-memory buffering, the data can have the risk of being lost or being inaccurate at any given time, so that people have this different operational costs. So after we actually collect those information by communicating with our customers, we can actually suggest a architecture solution, first of all, around Kafka as the pipelining backbone to our customers, and along with the different types of ecosystems for doing the management and operations.
For customers of Confluent or just these managed data, big data providers, what is the integration process like if you're trying to use several managed big data providers? Like you're trying to use Cloudera for one thing, maybe you're trying to use AWS for another, you're trying to use Databricks for another thing, you're using Confluent for Apache Kafka. What is the integration process like? Is it really difficult?
I think not, because actually, like you mentioned, like the Confluent and like Cloudera or Hortonworks and AWS, they are really at different tiers and different areas of a organization's data pipeline.
So mutually exclusive.
Mutually exclusive, I think, yeah. So like Confluent is mainly focusing on the real-time data pipelining. That actually makes the data being available to both the online and offline system that gets collected. where I think, Hadoop ecosystems is more on the offline batching processing world, where users can, really make use of the collected and pipeline data and get value out of this data using their processing logic, such as like some data mining or machine learning or, OLAP and the data warehousing computations. And where we also have a different layer beyond all those kind of systems, which is supporting the architecture or the machines or the clusters for supporting those systems. I think that is where providers such as AWS is targeting at. So in my mind, I think those systems are quite exclusive, and the ways of operating those systems should also not be conflicting with each other.
What is the typical experience for a customer at a company that he's using Cloudera and Confluent and Databricks? And yeah, sure, they're mutually exclusive, but is there a role for this type of managed big data technician, or are these do these services work well enough that you don't spend much time fixing things, and you get to spend more time just leveraging them, or what is the experience like for the end user on these sorts of platforms?
Yeah, I think for the user on the end platforms, first of all, they will have some the whole architecture solution people, which basically have the big picture of the whole pipeline from the real time to the offline world, and as well as underlying resource management, cluster monitoring, etc. And for Confluent, we actually provide such consultant services for users to build up the whole architecture involving Kafka as a real-time messaging system. And of course, when there is the data services have some examples, including some data lineage requirements, such as if I am actually looking at my HDFS and I want to know from which online data types in Kafka does my HDFS data blocks get generated, then they actually may need some cross-platform solutions or cross-platform services that can actually does this monitoring or auditing for the user.
Does it surprise you the way that the big data ecosystem has developed, where you have these different managed big data providers?
I'm sorry, can you maybe say that again? I don't.
Sure.
I'm not sure I get the question clearly.
Okay. Does it? So if you go back, I don't know I can't remember when the MapReduce paper was published, but you look at the MapReduce paper, and then the Hadoop world starts to develop after Hadoop is created. Does the way that history unfolded surprise you at all? It seems like the way that the Hadoop ecosystem unfolded was this, now you've got this collection of managed big data providers, and in order to build a big data platform, you configure all these different services. In the past, it seems like this would have been something that one company does, and you go to that company and you say, hey, do everything for me. But it seems to be this interesting development where you've got these different providers in the marketplace. I'm not saying it's a good thing or a bad thing. I just find it surprising. Does it surprise you?
I think, it was actually changing quite a lot as a trend. That, like you said, I think in the old days, we have this one-size-fits-all system where all kinds of data needs will go to this system, right? So for any data usage, we just say, okay, store that in a database or a OLTP systems and do all kinds of queries over it. But today we have seen this one-size-fits-all has been kind of broken because of two things. I think the first one is the volume of the data. And the second of it will be the velocity of the data generating and being consumed and being processed, as well as the variety of the data types that we actually generate with this high velocity. with those two trends actually has been driving the so-called the one size does not fit all principle, where we actually tend to build more specialized systems for different data needs instead of having one system that actually fits all processing requirements.
What is the future of Apache Kafka?
I think Apache Kafka has been, originated as a, messaging, PubSub messaging systems. But I do see that users have actually coming with more and more different usage of Kafka when we actually have talking to them. And I feel that moving forward, at least there are a couple of trends that Kafka can be used beyond a messaging system, sort of saying. So one thing is to serve as the source of truth, data storage for different kinds of distributed systems. Because Kafka in its virtue is actually a change log or transaction commit log, and based on this replicated and distributed transaction logs, different systems can leverage it to use for different needs such as data replication. So by leveraging this distributed and replicated transaction logs as a source of truth to do like consensus and to do data replication. And second needs is to actually serving it as, for example, the backbone for all kinds of online real-time data processing. Besides stream processing, we can also see usage of interactive data query systems that can also use Kafka as underlying real-time data storage systems.
So it's interesting. You said Kafka is the source of truth in many cases. How does Kafka as a source of truth differ from the use of a database as a source of truth?
Yeah, that's a good question. So I myself also came from the database background. So in many databases, right? So the data stored in the database itself is also backed by a so-called transaction log, or we call it the write-ahead log, where the log itself actually is served as the source of truth in the case of a failure or failure recovery scenarios. So the use of such a log is actually served to recover the data to some point when the system resumes, or we actually migrate the system from some host into other hosts. And so this concept of a log has been very important in actually a lot of the data storage engines. And because Kafka actually use this concept of a distributed commit log as its storage protocol, it can also serve as the same needs for those storage engines. I think as a source of truth for the logging of the records or the logging of the change behavior.
What is the future of Confluent?
Well, I think for us, we just want to be part of the Apache Kafka community. Be contributing to Kafka as much as we can to really make it as mature as the real-time messaging or the real-time storage system de facto choice. And at the same time, I think Confluent is also trying to build ecosystems for enterprise class stream data platforms that we can be profitable from this movement of the real-time data systems.
And what is Confluent's open source policy?
Well, I think right now, Confluent basically Confluent have like contributors and committers in Apache Kafka that is contributing open source patches. At the same time, we develop enterprise class stream data platforms. But I think for the core Kafka development, we believe that the development should really be happening at the open source Apache Kafka. Confluent will only be building the ecosystems or the supporting and operational tools to really support the users to use the open source Apache Kafka for their real-time data needs.
And how much time do the engineers at Confluent spend on open source software?
I can't maybe speak for other people at the company because like different people have a different focus. Like some of us actually have more focused as the enterprise products. Some of us are more focused on the open source. So for myself, I think more than 80% of my time is actually be spent on open source Apache Kafka development.
Is there much within the open source community? Is there much interaction between engineers from different companies? Like do the Kafka guys spend or do the Kafka guys at Confluent spend a good amount of time communicating with people at Cloudera or at Databricks, saying like, hey, here are some points where we need to integrate better, or does that communication, is that not necessary?
Oh yeah, that communication is definitely necessary, and we actually are doing it at a very healthy pace. So at Kafka, we have this Kafka improvement process meeting at a weekly basis, where all the developers or contributors from the community will meet electronically face to face to discuss about the development progress. So, and also for the project wise, we have like contributions from companies like LinkedIn, Confluent, Hortonworks, Cloudera on different aspects. So I think the communication is really well organized and is very healthy. And we actually meet and talk to people nearly every day and every week to discuss about the future development of the open source product.
It almost seems like much of the development process within these open source driven business models, it seems like these companies like Databricks, Confluent, Cloudera, the companies don't really seem to step on each other's toes, because it seems like the space of opportunity is so big. Each of these companies can focus on mutually exclusive opportunities. I mean, maybe there's some exception with like Cloudera and Hortonworks, but for the most part, it seems like that you can focus on a narrow open, like delivering a narrow open source project as a service, and like that can be a business. I mean, is that accurate? Does that seem accurate to you?
Yeah, I agree. I think that like for example, Hortonworks and Cloudera, they also contribute a lot to the open source Apache Kafka project, but I think business-wise, we really don't have too much of a conflict because the companies actually are focusing on different business areas.
That seems so much different than any other industry I can think of.
Oh yeah, that's an interesting scenario to observe. I agree.
What is the future of big data as a whole?
So for me, I mean, my personal take would be that the one size does not fit all trend will continue, such that people will continue to build more not more, but maybe much specialized systems for different kinds of storage as well as processing needs of different data types of data, and I think from a business point of view, that those companies that actually are focusing on different kinds of specialized systems will also emerge. And one observation, like you said, is that those companies may well coexist for sharing different kinds of customers, because of the areas they are focusing is quite different.
Describe your perspective on the movement from batch-based processing to stream-based processing.
Yeah, so I think in the past maybe 10 years of this big data movement, people have been mostly focused on the volume of the data, because that is actually the first big thing that comes when we really enter the new era. We see that different types of data has been collected at a much larger scale compared with the traditional data usage. But I think moving forward, as we have achieved, a very large volume of the data already, people will be gradually moving their focus to the velocity of their data, so that people will now ask that, okay, now I have this already large volume of data. My next question will be, how soon can I actually make those data available to my data analytics system so that I can really get value out of it? So I think that is also like a big opportunity for the real-time world to emerge in this big data movement.
And can you explain some of the trade-offs for a company that's looking to move a lot of their batch processing to stream processing? Like, how expensive is it?
I think the first thing that for the cost of such movement will be also the data migration, right? So for offline data processing, people tend to use like HDFS as the source of truth data storage to store their data for batch processing. And when they consider moving to real time, many of those data will better be migrated into online data storage systems such as Kafka. So that data migration will be one operational cost that people need to pay when they do this migration. And the second thing that I think people move to online processing would be, the logic of their computational patterns. Because in terms of batch processing, where users are actually more focused on processing a block of data at a time, for real-time processing, it is actually a much finer granular, such that people are actually focusing at one record at a time processing patterns. So this change of mind in designing their computational logics and application logics can also be something that people need to pay attention to.
So if I understand streaming correctly, and correct me if I'm wrong, but a lot of it's sort of like you take things that we used to do on disk. We used to use disk for, right? Like Hadoop, we use disk, and we move that functionality to end memory, so it's faster. Is that accurate?
I think it's maybe not like 100% accurate in terms of the definition, but it's a personal thing. So I think like in the past, when people talk about stream data, right, they really focus on the aspect that the data record can only be processed once. That is mainly because that you store your data, like you said, in memory, such that it can only be observed and processed once, and because that the new data will keep coming, we have to drop those data right after they get processed. So the focus of the streaming data is really on the one-time processing characteristics compared with the original DBMS, where the data is persistent at disk. You can access and query them whenever you want, right? But today, since we are moving to real-time data storage, also persisting them into a persistent storage such as like Kafka does, I think this kind of like aspect of streaming data processing has been blurred a lot, such that the user can actually do reprocessing as well, even if they are processing streaming data. On the other hand, people are more focused on the computational pattern, such that the streaming data is a consecutive processing of one record or a batch of record at a time, compared with original OLTP or data warehousing, or today the batch processing systems, where people will basically be accessing the whole data set all at once and do the query over it. So that is, I think, the more focus people are looking at today for processing streaming data.
And I know we're running low on time, but I'll just ask you one or two more questions.
Sure.
So the I want to talk some about the synergies between a streaming and a batch architecture. Are people building architectures in such a way where you've got elements of your architecture that are being constantly updated via streaming, and you are occasionally running Hadoop queries across that constantly updated stream data? Does that make sense? Does that make sense?
So let
me phrase this better. Let me phrase this way better. Okay. What are some synergies between a streaming and a batch architecture? Like, what are some systems where you would want to have this heterogeneity of streaming and batch?
Okay. Yeah. I think for streaming data, basically, again, it's like a consecutive processing where you cannot actually access the whole data set all at once. Instead, you will access maybe one record at a time, or a small batch of record at a time, and you have to basically make your processing logic to be adaptive to such a characteristic of data types. Where for batch processing, usually the data has already been available as a whole to the users, and the users can actually access them and query them from bottom up to get the whole value out of the data at once. But again, like you said, the data needs actually time to really be completely available and be queryable to the users, so that there will be a trade-off between the latency of data availability compared with the computational logic you can actually execute over your data to make value of it.
Okay, well, that seems like a good place to close. Thank you so much for coming on Software Engineering Daily. It's been a real pleasure speaking with you, and yeah, I'm a big fan of what you guys are doing at Confluent, and keep it up. So have a great day.
You too. Thanks, Jeff.
Okay. Yeah, thank you.